That's a ton.
I don't know what they're saying. So.
Man, that joke was so
All right. So today we're starting to talk about the model of the atom. All right. Today we're going to start talking about Dalton and Thomson's model, and then we'll finish it up tomorrow with Rutherford. But here is the model of the atom that Dalton had. It is a indivisible sphere. Okay, I think I may have mentioned it yesterday. Did I? Okay. So he didn't know about any protons. He didn't know about any electrons. Didn't know about any neutrons. He just said it is a solid sphere that's indivisible and it has a uniform density. So the uniform density is whatever this is. So make good rubber balls. So that was the initial model of the atom. Dalton came up with that. Then Thomson came along, and he had these cathode ray tubes in his lab. Now, actually last class said Grandma and Grandpa still have these type of TVs. The big boxy TVs. Or does anybody still have those big boxy TVs? Yeah, I finally got rid of my last one about 3 years ago. I'm so grateful. I remember when I first got married that the one TV that I had was huge, and I tried to put it in the back of my car, and I think I gave myself a hernia. So that was good stuff there, good memories. Oh God. Okay, so a cathode ray tube or a cathode tube. Here's the cathode end. In other words, what happens is on one end of the tube, it actually forms rays and moves to the anode, which is on the opposite side. And yeah, the positive end, very good. So we've got the negative end and positive end. Now, what's crazy about this is Thomson accidentally put a magnet nearby, and when he put the magnet nearby, this light was either deflected or moved toward the magnet, depending on what side the magnet was facing. I would assume that this was the positive end of the magnet, if I were a betting man, because when this came this way and he flipped it over, then the ray went the other way. What's that?
From the picture, it looked like some kind of weird liquid, and I got all kinds confused.
So it's a light beam, a particle beam. How's that? Gotcha. Welcome aboard. Adequate. All right, so if I had normal light and I brought a magnet up to my normal flashlight that was shining light out onto you, and I brought a magnet nearby, what's going to happen? Nothing, because our normal light doesn't have any charge. Photons have no charge. But this light did have charge because it was influenced by a magnet. So Thomson proposed that this light was generated by the excitation of, quote-unquote, Dalton's atom. And so there must be something in that atom or on that atom or somewhere around it that was being excited. And so he gets credit for finding the electrons. Now, he also did some other crazy experiments. Here, nothing, there's no magnet nearby. And then he would bring a magnet nearby and cause it to deflect or go to the magnet. And then he would bring in more magnet type things. Here he had a positive plate and a negative plate, and he actually got the light to do some roller coaster moves, I guess you'd associate that with. Again, they didn't have much entertainment back then, so this was the highlight of the day. I bet this guy had to show a lot of fun things there. All right, and so he noticed that the particle beam, as it went from the cathode to the anode, that it was a pretty fast-moving particle. And as he stared at this thing more and more, he noticed that there was another particle moving in the opposite direction, this way. So if we started these particles going in that direction, probably blue on blue is not a good idea, had these particles moving in that direction, and he associated that with a negative charge, what do you think the charge is when they move this direction? Positive. So he proposed that there was this positive particle that was also an atom. He didn't know what it was called. I don't think he was the one that came up with the term proton. And I'm not sure if he actually came up with the term electron, but that's where it led to. So he came up with proton and electron, or the particles, I should say. And the symbol for an electron, as we now know, looks like that, and it has a negative charge. Now, I guess back in the day, there was a very delicious treat, and he associated his model with this treat of the day. And it looks something like this, where you had your atom, and he had these particles kind of scattered throughout. This was his model. Now again, this is not what we believe today. At least I hope you don't believe that today. And he said it kind of looks like, where is it? Oh, here it is. A plum pudding pie. I'm not sure exactly if I would want to partake in such a delicious treat as that. But the plum pudding pie model is that, where the plums were kind of scattered throughout. And that was Thomson's model, where he had this sphere. So it's evolved from Dalton's dense uniform ball into this sphere that has these particles scattered throughout. Okay. Tomorrow we have this exciting conclusion, but I don't want to talk about it yet. So I do have a demo in the back, so let's go to the back. Fire? Kind of like fire, maybe. Did you find a plum pudding? There are electrons. This right here is a cathode ray tube. I have an anode and a cathode in there, and I'm exciting the cathode end of this tube, and it's attached or grounded to this metal pole here, which acts like a nice conductor. The green light within the tube here are actually electrons, and the electrons act like they're a stream of light or a path of light. However, if I take my magnet and I place it near this light, it actually bends the path of the light. Notice how it's without the magnet. It's pretty straightforward, but I bring it and it definitely influences. When I turn the magnet, it'll either scatter the particles there at the end. So even though it's going away, it's actually scattering them more than anything else. When I turn the magnet the other way, it actually bends down toward it. So this is what Thomson used to help prove that there are some subatomic particles that actually have charge. Now, normal light is not affected by magnets itself. So there's your examples of your electrons. All right, just to clarify, 2B. Now, hang on, just to clarify 2B, what this is saying is, okay, so you've got your charged plates, which I can be honest, I've never seen charged plates in my life either. But we can hypothesize that these things do exist. So if you had your charged plates, one being positive, one being negative, since it is a magnet, and if you run a beam that is, let's say, negatively charged, I'm going to let you answer, don't you say it out loud. Tell me what's going to happen when it passes through. Okay, I'm not going to answer that for you. And also, if we had a particle beam that was positively charged, if you pass it through these plates, what will it do? Okay, so that's what that question's asking 2B.